So in this video we're going to look at the chain rule for multivariable functions where we have a function of x and y, but x and y are functions of a single independent variable. So if you think back to the chain rule for single variable functions, we're really looking at function composition, d dx of f of g of x, and we take the derivative of f at g, and then we have to multiply by the derivative of g. So what's going to happen when we're working with a function of two variables, f of x, y, is we're going to have to take the partial derivative of f with respect to x, and then if x is itself a function of a single independent variable t, to get the rate of change of f with respect to t, we have to then multiply by dx dt. So it's partial f partial x. What's the rate of change of f as a result of a change in x times the change in x that is a function of a change in t. And kind of a way to help you think about this, you think of hey, those look like they're cross-canceling. It's probably naughty to think of it that way, but you get a rate of change of f with respect to t, but this part of the change in f is as a result of the change in the x direction, and then you have to add to it the change that's a result of change happening based on things changing in the y direction. So we do partial f partial y. If y is a function of t times dy dt, we get the rate of change of f with respect to t that is because of how things are changing in the y direction. And the sum of the two changes, the change that's as a result of change in the x direction plus the change that's a result of the change in the y direction, the sum of the changes gives you the total rate of change because of t. So an example of working one of these out, we'll let z be equal to x times y squared minus x squared, where x is changing as a function of a single variable and y itself is also changing as a function of a single variable. So if we want to get the rate of change with respect to t of our function z, so if we want dz dt, it's going to equal, it's got to be the rate of change of z as a result of x, so partial z partial x, times what's the rate of change of x because of t, and then we need to add to that the partial z partial y, what's the rate of change of z because of y, times how is y changing as a result of the change in t. So we need to calculate each of these derivatives. So if we first think about z equaling x y squared minus x squared, then partial z partial x, or f sub x, is going to equal, we hold y constant, so x times y squared, the derivative with respect to x will be just y squared, because we treat y squared as the constant coefficient on x, and then minus the rate of change with respect to x will be 2x, so there's our partial z partial x. And then we could calculate partial z partial y, which we can also denote as f sub y. The rate of change here with respect to y is going to be 2, the 2 will come down, so we'll get 2x times y, and the rate of change of x minus x squared with respect to y is 0, so there's our partial derivatives with respect to x and y. So you can start to build your derivative over here. I have partial z partial x coming from here. I'm going to get a y squared minus 2x. But then I'm going to need to multiply the rate of change of x with respect to t, so we'll need to calculate that. And partial z partial y is right here. It's 2xy, so I get 2xy. And then I'm going to need to pop in the rate of change of y because of t. So if x is equal to cosine of t, then dx dt is going to be equal to minus the sine of t. So the dx dt goes right here. We get times minus the sine of t. And then we have y equaling e of t, e to the t, sorry. Then dy dt is just equal to e to the t, that our favorite derivative to take. e to the crap equals e to the crap. And then maybe clean things up just a hair. I've got a minus sign here, so maybe I distribute that minus into the parentheses. That'll change the order of the subtraction. And then I have sine t plus 2xy times e to the t. And then what we want to do is express dz dt completely in terms of t. So because x and y are functions of t, if we're going to do dz dt, it makes sense to then substitute. So 2 times x, but x is just the cosine of t, minus y squared, but y is equal to e to the t, so e to the t squared is going to be e to the 2 times t times the sine of t, plus 2 times, I'm going to get rid of this to give myself some space, 2 times x, but x is just the cosine of t, and we have e to the t times a y right here, and y is just equal to e to the t. So e to the t times e to the t is going to be e to the t plus t is e to the 2t. And then that looks like it's pretty well simplified. We could have gotten this same result that we did by using the chain rule. So the chain rule result that we have right here, we could have gotten by just doing an initial substitution. So the other way we could have gotten at this is, see if I have enough space to work it out the other way. The other way we could have gotten it would have been to make the substitution right at the start. So we could have replaced x with the cosine of t. We could have replaced y squared with e to the t squared is e to the 2 times t, minus the x squared, which would have been the cosine squared of t. And then we could have just taken the derivative of this with respect to t. So we could have done d dt of both sides of this, because I've converted what was a function of 2 variables, right? I started with z of xy. We've converted it into a function of a single variable. And then we could have used our regular single variable techniques to find the derivative.